Good morning, everyone. My name is Tommaso Macri from QuEra Computing. To the training session for our South Korean community. And we want to welcome all of you to the tutorial on neutral atom quantum computing sponsored by QuEra and the POSI Supercomputing Center located in Perth, Australia. So I'm happy to introduce my esteemed guests for today's session. My colleague Minho Kwon, who is the head of laser systems at QuEra, Jonathan Wurtz, the quantum solution lead, and our two partners from the POSI Supercomputing Center, Pascal Elai and Edric Medvedev. So with this, let me go briefly through the agenda of our session today. We will start with some brief introduction about QuEra computing and some basic facts regarding neutral atom quantum computing. Then we will start our deep dive on our first modality that we can realize with neutral atoms, which is the analog mode. This part will be led by Pascal and Edric. And then we will focus on digital quantum computing. And this part of the tutorial will be led by my colleague, Jonathan Wurtz. We will conclude our 2-hour long tutorial with some final considerations and conclusions. So let me start by saying a few words about QuEra computing. QuEra is a quantum computing company that is based in Boston, Massachusetts. We are at a bike ride from the campus of Harvard and MIT. And our mission is to build and productize quantum computers based on one of the technologies that are relevant to perform quantum computation, which is neutral atoms. It is also one of the most promising approaches for the reasons that we will explain throughout the tutorial, as with respect to other platforms that are available currently on the market. Our first quantum computer that you see here on the right part of the screen on the video was first deployed on the AWS cloud in November 2022. So it completed already more than 2 years of operation. And it is used today to solve problems in simulation, machine learning, and optimization. And we will hear more from both Pascal, Edric, and Jonathan in a few minutes. So with this, I would like to pass to give the word to my colleague Minho to say a few words regarding this tutorial in Korean. And with that, I will see you in a couple of minutes. So please, Minho, the floor is yours.
Yeah, thank you so much for nice introduction, Tommaso. Hello, everyone. My name is Minho, and I'm the head of laser systems in QuEra. I've been with QuEra for 3 years, and at the moment, I'm the only Korean employee. And I was told that the major portion of today's audience are actually very familiar with Korean. So here I am, and I'll be making brief remarks in Korean from now. 안녕하세요. 큐에라 컴퓨팅의 권민호라고 합니다. 오늘 튜토리얼 와주신 분들 정말 감사드리면서 오늘은 중성원자를 이용한 아날로그 컴퓨팅과 디지털 컴퓨팅에 대해서 더 알아가실 수 있을 거라 생각됩니다. 그럼 기술 프레젠테이션으로 넘어가기 전에 큐에라에 대한 간략한 소개와 이번 달 말에 있을 한국 관련 행사에 대해서 잠시 알려드리고자 합니다. Could you go to the next slide, Tommaso? Thank you. 그래서 저희 QuEra 컴퓨팅 본부는 하버드, MIT와 인접한 보스턴에 위치해 있고요. 최근에는 일본과 영국에도 이제 지부가 이제 열려 있습니다. 그래서 이제 글로벌 기업이 돼가고 있네요. 그래서 저희는 저희가 생각할 때 최유망한 기술이라고 생각되는 중성원자 기반으로 양자 컴퓨터를 만들고 있고요. 제1세대 아퀼라 프로세서는 아날로그 컴퓨팅을 지원을 하는데 2022년 11월, 그러니까 약 2년 반 이상 동안 클라우드를 통해서 공개적으로 서비스를 해드리고 있습니다. 그리고 최근에는 디지털 방식으로 동작하는 컴퓨터를 일본에 설치를 하고 현재 조정 중에 있는데요. 이와 같이 중성원자 분야에서는 과학적 그리고 상업적 양 방향으로서 선도적인 역할을 하시고 있다고 생각하시면 될 것 같습니다. 그리고 현재 활용이 많이 되는 분야는 최적화 문제 해결인데 오늘 튜토리얼 웨비나에서도 이 부분을 커버하게 될 것 같습니다. 네, 그리고 사실 오늘 양자 컴퓨터에 대해서 이렇게 많이 배우러 와 주신 분들께 양자 컴퓨터를 하나씩 들여서 직접 체험을 하면 좋겠지만은 어, 네, 사실 경품이 준비가 되어 있습니다. 토마스, could you go to the next slide? Thank you. 어, yes, okay, great. 그래서 양자컴퓨터 배우러 오신 분들께 한 분께 양자컴퓨터를 하나씩 드리면 좋겠지만은 아직 그럴 수는 없고 대신에 양자컴퓨터 모형을 오늘 오신 한 분께 드릴 예정이니까요. 끝까지 경청해 주시면은 감사하겠습니다. 그리고 한국 분들이 QLA에 많은 관심을 갖고 있는 걸 알기 때문에 이런 웨비나뿐만 아니라 더 긴밀한 협력을 위한 노력도 하고 있는데요. 토마스, 그죠? Yeah, thank you. 그 일환으로 이제 약 2년 전에는 카이스트 세종시와 함께 3자 간 양자산업 육성을 위한 업무 협약을 맺은 바 있습니다. 또한 매 여름 한국 서울에서 열리는 퀀텀 코리아 전시에도 참여를 하고 있는데요. 토마소? 야, 땡큐. 네, 올해에는 저를 포함해서 아유무 이마이 큐에라 일본 지사장과 그리고 토마소 맥크리 전략고객 총괄 이렇게 세 분을 만나실 수 있을 것 같습니다. 그래서 밑에 보시면은 이제 퀀텀 코리아 기술 발표를 포함하여 다른 셀트라이트 이벤트가 여러 개 있는데요. 이런 다른 어, 함께 열리는 주변 행사도 와주시면은 많은 걸 배워가실 수 있을 것 같습니다. 어, 네, could you go to the next slide, 토마스? 네, 그러면은 오늘 많은 걸 배워가시길 바라면서 더 궁금하신 것 있으시면은 저기 Q&A 기능을 통해서 질문을 해주시거나 퀀텀 코리아 전시 때 6월 24일에서 26일 사이 저희 전시장에 오시면은 저희 그 큐에라 가는 세 명이 궁금증을 해결해 주시도록 하겠습니다. Okay, thank you everyone for listening. And now I would like to hand my mic over to Tommaso to move to the next session. So Tommaso, you can take it from here. Thank you.
Thank you so much, Minho, for this very nice introduction for our Korean audience. I will go back, we will switch back to English now. And with that, I would like to give a very, very, very broad and introductory perspective on why why doing quantum computing with neutral atoms. So there are several reasons in principle. First of all, neutral atoms are essentially nature's perfect qubits. We use atoms that are all identical. In particular, our favorite atomic species is called rubidium-87. They are identical, pure, and in principle resistant to noise. And differently from other platforms, in particular from qubits that are kind of artificial, they essentially respond to external fields all in the same way. The second property is related to scalability. Nowadays, we have systems with hundreds of qubits, but there are already demonstrations with a few thousands of qubits, and we expect to be able to scale these systems up to tens of thousands or even hundreds of thousands of qubits without requiring complex interconnects. Then there are some important capabilities, for example, the possibility of reconfiguring layouts in real time and moving qubits within the computation area, so that we can essentially perform encodings that are extremely efficient and potentially perform easier quantum error correcting operations without the standard limitation related to systems with fixed topology. Last but not least, our systems operate at room temperature, without any types of cryogenic, therefore reducing both the complexity and the footprint of the machines. All this technology was essential to design and productize our first generation quantum computer, which is called Aquila, a system with up to 256 qubits, which is still the largest quantum computer available on the market per number of qubits. Then the other important thing from the engineering perspective, over the past couple of years, we increased the availability window or the uptime of the system from about 10 hours at the beginning in November 2022 to more than 100 hours per week currently. We use this system to explore a number of applications, either through the access with AWS or through direct access for our premium customers. And the problems that we are able to solve can be essentially classified in three main areas. The first one is machine learning or quantum machine learning to tackle tasks for classification or regression and prediction. And in particular, we will hear more during the presentation about one of the methods that we recently explored or introduced, which is called quantum reservoir computing, therefore generalizing a well-known algorithm in classical machine learning, which is just called reservoir computing. The second class of problems is called combinatorial optimization. And here, what I just want to mention, then leave the word to my colleagues, Pascal and Jonathan, to go more into the details. There are some important native problems that can be explored with this platform. This class of problem is called the maximum independent set, but I can already mention that there are also other combinatorial problems, such as, for example, cubo problems that are very relevant for commercial applications that can be mapped into native problems that can be solved with our machine with some overhead on the number of qubits with respect to the number of variables that define the initial mathematical problem. And finally, the last class of problems, which is called quantum simulation, inspired by the original ideas of Richard Feynman back in the 80s, it is particularly important to start to solve problems that are inspired by scientific applications. For example, studies for fundamental theories in physics, for example, lattice G theories, or equilibrium or non-equilibrium properties of matter, or even problems that are inspired by chemistry or quantum chemistry. The second generation machine, which we recently installed at this important research center located right outside of Tokyo, Japan, called AIST, is called Gemini. It is a gate-based quantum computer, still functioning with the same technology of neutral atoms. It has 256 qubits, and it is particularly relevant or ideal for the integration with current and future HPC centers. The picture that you see on the right is a picture of the machine that we recently installed at AIST, alongside the so-called ABCIQ supercomputer that hosts a few hundred GPUs from NVIDIA, thereby creating the first quantum supercomputing system available currently in the country. The other thing that is worth mentioning is that thanks to the type of technology that we employ, which is neutral atoms, the machine actually requires very little power. The estimate is of the order of 7 to 10 kilowatts of power, which is much lower than other types of technology that are currently available on the market. All these systems, for the second and future and upcoming generation of quantum computers, are particularly relevant to tackle complex applications that require, as for any type of quantum technology or quantum computing technology available currently, a fundamental layer that is related to quantum error correction. In regard to quantum error correction, I want to mention that definitely QuEra is considered to be the leader in this space. And thanks to the both the theoretical and the scientific and experimental discoveries and demonstrations that we have done over the past couple of years, together with our main collaborators from Harvard and MIT, some of these discoveries were actually um, defined as the breakthrough of the year 2024 by Physics World. In terms of applying all this technology to partners and to basically start working with partners, customers from across industry, academia, and government, at QuEra, we believe that we basically can start be very effective along three main pillars. The first one is essentially to work with partners to install quantum computers and access them either through cloud services or through on-prem deployments. All of this comes with a very high-level installation support and community development work done by our scientists and engineers from QuEra. And it is targeted to do essentially either collaborative research together with our scientific team within the company to target problems, for example, in quantum error correction, which is a very important task to make these computers useful for applications, as well as to start looking at important hybrid algorithms or applications, and we will hear more about that throughout the rest of the tutorial. The last area that I would like to cover or to mention is the idea of application co-design. The current quantum computers that we have available today are essentially not powerful enough or too noisy in order to start looking at practical application in a scalable way. One way to approach or to overcome this barrier is to start looking also or to start designing applications that essentially match the current capabilities of quantum computers. So in a way, at QuEra, we believe that we have to tackle the problem of approaching and developing useful applications both through a kind of bottom-up approach, essentially designing and realizing more powerful hardware, but at the same time, or in parallel, essentially applying a kind of top-down approach where we match the capabilities of quantum computers by very fine-tuned applications. And we would be extremely happy to learn from our customers as well as from the participants and attendees of the events like this one. What are the needs in terms of application development in order to make this process even more productive and effective? One way to basically broaden the community around neutral atom technology, especially from the perspective of QuEra, is through the very dedicated and specific partnerships. And in order to be extremely effective on that, last year we created the so-called QuEra Quantum Alliance that by now includes more than 20 members from all around the world and across several business verticals. So what you see here is the list or the logos of many of our partners that include system integrators, quantum computing companies, as well as companies that are dedicated to the development of software applications and hardware. So with this, I would like to give the floor to my colleague Pascal, that will start the first part of the deep dive on neutral atoms focused on analog quantum computing. Before giving the word to Pascal, let me highlight that you are very welcome to start asking questions on our chat. Some of the questions will be answered directly on the chat or in the Q&A session. Others will be selected for a direct or dedicated response live. In any case, I want to incentivize, all of you to start to ask questions because we want this tutorial to be as interactive as possible. And for those that cannot really follow the presentation, all the presentations during for the next hour and a half or 2 hours, the tutorial, the webinar will be available on QueRa's YouTube channel. So with this, I would like to conclude here. I will see all of you during the conclusion. And thank you for listening. And Pascal, the floor is yours.
Thank you, Tommaso. I'm gonna, oh, there we are. Hold on. Screen share. So hello, everybody. Anasayo. So I'm Pascal Jahanalahi at the Pawsey Supercomputing Center. I am the Quantum Supercomputing Research Lead at a supercomputing center based here in Western Australia. And my colleague Edric will also give part of the talk, and we'll give you a kind of a lead in some problems on using neutral atoms and how to use them to solve actual, in principle, real-world problems. But before I go on, I thought I'd just acknowledge country. So it's a tradition here in Australia to acknowledge the traditional owners of the land. And Perth is located on Nugar Wajak Buja or Nugar Wajak country. So Ningalik Kadich Nugar Mut Kain Kadich Nija Buja. And this is acknowledging that the Pawsey and its people, like the people at Pawsey, are located in Western Australia in Perth on the lands of the Nugar Wajak people. And I'd like to pay my respect to their ancestors and elders, past, present, and future. I thought I'd throw this obligatory slide up to give you a context. Like, yes, we Pawsey are one of the QuEra partnerships. Actually, just beside Tommaso is our CTO, or an acting director for the Quantum Innovation Hub, Hugo Vereto, sitting beside everybody else at QuEra. Very much like CASTE, Pawsey is interested in the integration of quantum computing with supercomputing. And so I figured it's good to provide a bit of context of what Pawsey is and what we're doing in the quantum computing landscape. It gives you a sense of what we're aiming for when we're talking about the QuEra collaboration. So Pawsey is the Supercomputing Research Center. It's a national high-performance computing center based in Perth, Western Australia. We're a Tier 1 center. We're actually an unincorporated joint venture between universities, so the major universities in Western Australia, the federal government, the state government, to essentially enable scientific computing. So we strive to be at the cutting edge of technology and accelerate scientific discovery through world-class supercomputing and infrastructure and expertise. And our staff is about 60, so we're a small group of people, but we have one of the largest computers in the Southern Hemisphere. So I mentioned scientific computing. It's kind of important that our expertise is really to enable all types of scientific computing that also have some industry applications. So looking at molecules, chemical modeling, astrophysics. We are involved in looking at how galaxies evolve. People are looking at also AI, bioinformatics, even fluid dynamics to look at like safeguarding coastal regions. That is sort of the remit of what Pawsey does. We are involved in national leadership as well. So Pawsey actually was involved in one of the major projects, one of the first deployments of a quantum computer at a data center, which was Quantum Brilliance. They're an Australian company, and they actually came to Pawsey to try to see if we could collaborate with them. So we're very keen on trying to grow the ecosystem of quantum computing. And one of their founders actually won an award. We were also involved in quantum chemistry, so not quantum computing chemistry, but quantum chemistry, which recently won a Gordon Bell Prize. So that's the equivalent of the sort of Nobel Prize in computing, a large-scale quantum computing, computing prize. And in this case, it's molecular dynamics. And the team is based in Australia, and they worked with Pawsey as well as other centers to get their code to do exascale compute and solve some really challenging molecular dynamics problems. So that's sort of where we're in. We're also a very diverse group of people. We really like to make sure that we also encourage lots of young people. So we have internships programs. That's sort of Pawsey's goal. And now I'm going to focus on the quantum computing aspect of Pawsey. So Pawsey's got this Quantum Supercomputing Innovation Hub, right, which was started up by a grant from the government. In its platform, it's meant to focus on a collaborative approach to quantum computing and accelerate scientific breakthroughs and prepare researchers for quantum computing, right, the impending quantum revolution. And so we're trying to skill ourselves, skill the community, and provide all the infrastructure that could assist that uptake. The team shown here, we're a small team. So myself, Edric, there's Shusen, Casey, and Ugo. Casey is a researcher at University of Western Australia, as well as a POSI staff member. And we are working on a variety of things related to integrating quantum computers with classical computing and also doing algorithm exploration. So we have the integration of HPC and quantum computing. We have quantum computing simulation, right? So as Tommaso mentioned, the scale of quantum computers right now they're growing, but you can still have some challenges because they're noisy. And so simulation is an important part of algorithm exploration. And we also are assisting in quantum acceleration by doing quantum simulation at large scale, at supercomputing scales, something that's typically not done in the quantum computing sector. But we also are looking at algorithm development in both near-term and far-term hardware, which is what we'll kind of go into when Edric shifts. But we also do educational stuff. So we actually have innovation, education, inspiration. Tommaso mentioned 3 pillars for QuEra. The Quantum Supercomputing Hub also happens to have 3 pillars, where we're looking at really trying to drive innovation internally, externally, in collaborative projects. Education, so we're really trying to build the Australian ecosystem through collaborative projects at the sort of research, university level, but we're also trying to assist inspiration, so getting younger kids exposed to quantum computing algorithms and quantum computing concepts, even in high school. Those are the pillars. In terms of innovation, the big one is that I kind of led to the start of the Quantum Supercomputing Hub. I mentioned before, Quantum Brilliance, they have a diamond-based technology. They were very keen on seeing if, even if they have a limited number of qubits, to see if they could deploy in an actual data center, and what we could learn also as a supercomputing center about that physical deployment. That actually won a technology award for the deployment of the quantum computer actually in the data center. And it's a very interesting challenge. Tommaso mentioned, he showed a nice picture of Gemini. In this context here, the box is being worked on, that there's a sort of a simple rack, but it's sitting beside other computers that actually do computing. And that's actually a real challenge because they generate vibrations, they have noisy fans. In this case, the computer that's just sitting in front is actually a supercomputer dedicated to processing of radio astronomy data. It had GPUs, the GPUs had fans. When it was processing, it was vibrating the actual rack of the quantum computer. They had to go through the process. So it's a very interesting process. One of the things that actually has to happen to really integrate the stuff for low latency communication. We're also looking at democratizing quantum access with AWS. I'll go into that in a bit more detail. But we actually got dedicated NVIDIA's latest at that point, latest super chip, Grace Hopper, right? Dedicated to quantum computing simulation. So we could assist researchers in exploring algorithms and trying them out without possibly not having direct access to real hardware, just so they could scale up in algorithms and see if they work well. I mentioned the education and inspiration. So one of the interesting things that I think is quite critical is we ran a boot camp for researchers in industry, but not quantum computing experts. So everybody in that picture, besides myself, and I think Edric's in that picture somewhere as well, were not people who actually had any expertise in quantum computing. They were people who were experts in other scientific domains like bioinformatics, chemistry, computer imaging, who were interested in learning, is it useful to do any quantum computing in the near term or far term, right? They didn't necessarily have the literacy to have that exploration. And we really want to build on that because that's how we get to real world solutions. The other one was a cool and fun day doing a World Quantum Day event for kids. It's a stop motion picture that the kids had fun learning about quantum computing concepts. We explained it to adults, high school kids, primary kids, tons of activities and so on. So it's really to inspire the next generation, to get other people interested in quantum computing, which requires a different skill set than standard computing. So I just want to mention the quantum computing simulation challenge. Part of this is just that it's a real challenge in terms of memory, but also scaling up compute, where you can really get to things that require, things that are the size of Cetonix for 50 qubits or so, 40 qubits or so, you're really looking at large-scale simulations requiring large-scale computing infrastructure. So one of the things that in policy we view, right, is quantum computing is an accelerator to standard computing technologies. So it'll be part and parcel of the next supercomputing infrastructure. But we want to make sure that we can also test everything. So you require supercomputing infrastructure to also test how things are working. So we look at developing, as I said, we had this cluster called Ella, dedicated to looking at developing software for quantum computing simulation, because the current landscape is challenging. I'll skip Ella. We've got a couple of different projects really aimed at quantum computing simulation, and specifically so that people can take those libraries, those specific software packages, run their algorithms to test them, that they would also normally scale up reasonably well. So it's providing a bit more of the quantum computing landscape in the software simulation side, but it's an important step. Another real important step, and I'm going to skip here, is orchestration of hybrid computing. So we really want to integrate quantum computers with supercomputers. So Posy has developed Qubit Bridge, which is meant to do this orchestration, right? Taking all of the stuff that we have in terms of the HPC center and being able to accelerate quite simply to a quantum computing device, which allows you then to have a multi-QPU, multi-GPU, multi-CPU dynamic workflow, which is essentially what you want to do at the end of the day, right? So once we get to quantum computers at scale, a quantum computer itself will not necessarily solve an entirety of a problem, but it will be very important to accelerate portions of the problem. And so we really feel that the idea of hybrid computing and lots of frameworks to essentially assist that hybrid computing and also assist fast prototyping is kind of a critical step as well. And actually, I'm working on this to integrate the blockade API. And so I'm working on one which will then be able to happily chat with any remote QuEra device in principle, and also run on any HPC system. So we can do this real world challenge looking at, let's say, maybe machine learning, and then say that portion of the machine learning workflow is useful to accelerate. Maybe we might look at quantum kernels. You might want to integrate that to accelerate some classical machine learning techniques, which also usually are part of a larger classical workflow, and get that running. And so this is just a quick screenshot of something that actually ran 4 QPUs, so 4 quantum computers, essentially 4 quantum processors. They're all running as virtualized services that do simulation. But in principle, if you pointed the remote to a different remote that was a real device, suddenly you have a workflow that, in this case, in this context, used several GPUs, several hundred CPUs, and several QPUs, all dynamically solving different problems. So there was shot parallelization, there was essentially different circuits being run on different QPUs, and this can scale up and maybe add some extra complexity, which we feel is kind of important going forward. I have a movie, but I'm not going to show that because I want to make sure that we leave enough space to also dive in a bit more into the things that we're doing with QuEra. So democratizing access. This is also really important. So I assume that the challenge is also faced by everybody in the world. One, Aquila is awesome, Aquila is up. There's one Aquila, right? There's not that many quantum computers. They have limited access compared to classical compute, right? If you think of AWS, QuEra is actually on AWS. You might, if you want to access that device, it's accessible, but you have to generate an AWS account, have a budget for it, spend some money, and that can limit the people who can actually get access. And so we want to democratize access so that anybody with good ideas can in principle get access. So we've been working extensively with AWS to essentially provide a policy access. So instead of having an AWS account and paying AWS budgets, it's a merit allocation scheme. You propose a science project. Posy says, yes, that's a good science project. We set up a budget. There are budget controls. And then users can suddenly access a wide variety of quantum computing technologies, but also quantum computing simulation. And that allows them to test real algorithms on real world devices while after also running quantum computing access, and not have to worry about management of budgets and accounts and chasing up. We kind of provide all of that. That simplifies a researcher or industry partner life because they don't have to do this. They just need to have the POSI username and password and a budget. Right, so we think this is going to be very useful for easing access barriers. Now, I mentioned POSI, right? So it's very important, POSI. We're very keen on collaborative projects because we really feel that this is space to do it in, and that's why we actually are part of the Quantum Alliance with QuEra. We keep growing partners because the work we're doing is of interest, and also the work that other people are doing is of interest to us. So we want to kind of grow this ecosystem. And that's why really we kind of joined QuEra. So QuEra has been very good at working in a very collaborative fashion, open fashion, with researchers and policy staff to kind of look at near-term projects that can run on the current systems, but also forward-facing as well. And we collaborate with other centers across the world. So we've got researchers based in the University of Western Australia. There's the Australian Commonwealth Scientific Industry Research Organization, so essentially the equivalent of KAIST. We've got a bunch of different partners as well. We're developing a relationship with ACE in Japan. And I would like to actually encourage people. So we give you a chance to explore Aquila. And there is the Quantum Korea. But if you also have an idea for a project, you can actually reach out to me, and you can reach out by the webinar to actually see if there's a possibility of having a collaborative project between POSI and Research Institute of Korea and QuEra to actually get access to real-world technologies, to work on a scientific paper results. If you have ideas, I encourage you to reach out because we would like to keep growing the ecosystem. So in terms of analog computing, so we mentioned, it was already mentioned, optimization, quantum machine learning, and quantum systems modeling. In our case, right, so we actually have definitive projects that involve Jonathan. They actually involve some other QuEra people like Milan and Jing to work on optimization problems, to work on quantum machine learning problems. And they're not just like generic ones. Like we are really looking at using reservoir computing for looking at radar imaging data and also health data. So the quantum machine learning aspect, there's a project looking at predicting lung function based on blood marker data. And it's a very interesting project that kind of possibly is well suited to the reservoir computing aspect. So we're kind of very interested in seeing if there's a near-term real-world application that can happen. And it's happening because we've got policy staff involved, we've got QuEra staff involved, we've got researchers at the University of Western Australia and the Department of Health involved, all interested in saying, well, let's see if we can do some quantum acceleration of something that already kind of exists. And so there's open science research goals, but there's also sort of longer term real prototyping possible as a possibility. So I think that's really kind of part and key of the collaborative aspect that we have. Quantum system modeling, looking at, I mean, my background is computational astrophysics, so I love the idea of trying to look at early universe fields and quantum systems in those states, but we also have looking at just essentially general quantum systems with researchers who are based in Singapore and the UK, a couple of different institutes looking at master equations and quantum baths and how systems respond. So it's a wide breadth of projects that POSI is involved with that also touch on kind of all the aspects that Aquila could be very useful for. And it's kind of an interesting thing. We didn't necessarily aim to spread out to these projects, but we all had different ideas and these projects kind of naturally arose. So with that, I'm going to actually hand over to Edric because he's been leading the specific project on the POSI side for scalable techniques in quantum optimization. Edric, would you like to take over? And just let me know when you need.
Thanks, Pascal. Am I coming through okay? Great.
Yes.
Fantastic. Yeah, over the last few months, been lucky enough to be working with Jonathan and Jing over at QuEra to sort of research methods for, well, efficient state preparation on the analog Aquila system. And this is really motivated by this particular algorithmic structure that we see a lot in combinatorial optimization, which is a example we'll walk through shortly. Sorry, Pascal, are you able to stay on? Thanks. Now, these algorithms, they have this layered iterative structure where the problem structure and how we get our qubits to interact and couple plays a very fundamental role in the type of convergence or speed up we can see. And one lens for analyzing and thinking about this ability to produce convergence is the continuous time quantum walk, where you can see in the lower right there. So that's actually a visualization of each of the possible states of a system of qubits that have been coupled together. So the coupled is in a sort of a transition between one state and the other, and we're letting our quantum system evolve through time. And you can see it sort of moves through the graph a little bit like a random walk, except because of the quantumness, we get interference effects. So that's the thing that's leading to that oscillatory behavior. And really, those interference effects are key to producing that convergence. So we've been really just looking at these quantum walks as a tool for benchmarking the scalability of these optimization algorithms, and also as a tool for preparing states that are relevant to these optimization algorithms. Next slide, please, Pascal. Yeah, so here we can see some of the actually early results where we're just looking at the type of amplification of a target state we're able to produce with these quantum walks, and the lower the lower purple dashed line is what we might expect with using an algorithm called Grover's search. It's a very famous algorithm that gives a quadratic speedup. And the lines above is the amplification or convergence we're seeing using a quantum walk over the types of graph structures that we're able to easily produce on Aquila. And seeing our early results sort of show that that does actually scale quite nicely on this analog hardware. So with that, actually, we'll move over to a notebook. We'll actually walk through what it looks like actually using analog mode neutral atoms quantum computing to solve a practical problem. So I'll just share my screen. Great. So the Jupyter notebook that I'll be walking through is actually hosted in this repository that I'll put into the chat.
Hendrik, I think we have a quick question from one of our participants. Maybe Miho, can you translate the question and for Hendrik and Pascal, and they probably can answer in real time before we deep dive on the Hamiltonian?
Sounds good. So there was a question about the graph in slide number 29. So the question is, what's the reason for dividing Aquila, even, odd, and case. So Eldrick, would you be able to go back to the slide 29 you shared earlier?
Yeah, great question. I'll
me
just
do that.
share the.
I'll share the PowerPoint because I have it up already.
Right.
And let me go full screen. Continue to share. Can you see that?
Yes.
Yes.
Oh, there you go.
Mm-hmm. So actually,
Right.
Pascal, if you could step back one
Sure.
slide.
I'm gonna go to the graph.
Yes.
Cool.
So the results we're looking at there are for a walk on the graph that we see in the lower right of the screen. And this is essentially the Hamiltonian, or the graph that you form using a ring of I think this is 7 there neutral atoms. So if we arrange these 7 atoms in a ring, and depending on whether or not we have an odd or an even number of qubits, we end up with sort of a very sort of a different number, or a different variations of the same general type of graph. Uh, Exactly why? Well, I think that might become more clear as we go through the notebook, but essentially that's the difference. So we have slightly different topologies resulting from whether or not we have an odd or even number of qubits. And as a result of that, the parameters that we need to lock in to achieve that amplification follow similar but distinct trends for the odd and even qubits. So if you go to the next slide, please, Pascal. Yeah, so if we were to plot the parameters that we're using, so the walk time and a couple other aspects, you would see distinct lines for based on the odd or even.
And just to make sure that's clear, right? So it's the optimal parameters in terms of pulses and placement, but usually pulses, and effective walks as well in the quantum walk setup that have this odd even split. And so this is also doing some optimization to figure out what those parameters are, checking the amplification you'd get out of the blockaded setup in a noiseless sense. And then here you have the equivalent with Aquila. And so the reduction in amplification in part is because obviously Aquila isn't perfect and there are some noise that kicks in, but with some possible extra bit of accounting of noise, you could maybe pick up better amplification by kind of rejecting some states. But this is the difference that you see between here and here and here and here. And then as a reference, for those of you who are familiar with Grover's search, this is what Grover's search would do. But again, this is a simulation, if I remember, Edric, right? You just did the pure just standard simulation of Grover's search and the amplification you get out of it.
Mm-hmm. Noiseless.
Yeah, noiseless. Yeah. It's not like Grover's trying to account for the noise in Aquila. This is just ideal qubits. And then you do a standard Grover search, and you can see how much of an amplification you get in the particular space that you're looking at. And I will stop.
So I suppose
Yep,
it's really that we're looking, at least here, at one particular aspect of a scalable quantum algorithm. That in particular, that's using interference effects with non-trivial quantum dynamics. And if we want to use those core elements of a quantum computer to solve problems at scale, we should be able to see them scale efficiently, over the range of qubits that our device is able to use, or at least as far as possible.
Yeah. And just note, so this is the maximum independent set state, so MIS state that we're looking at, but that's not, you're not beholden to this.
Yeah.
It's just this particular example.
We'll be talking a little about MIS in a moment, so
thank you. So just like one quick follow-up from the same question, the same person is if the noise issue goes away, then would you don't need to like it's not unnecessary to distinguish even and odd cases?
So the good question. So the even and odd case is actually it's like a fairly sort of fundamental property of the particular topology that we're looking at. So particular arrangement of atoms and the type of interconnectivity that generates in the Hilbert space, like between all of our possible quantum states. So in fact, say that the fact that there is this distinction is a good thing. Now you might look at that plot and we see that the even n it looks like it's slightly below the odd n. But every time we add another qubit, we're actually increasing the number of states in our sort of quantum space, Hilbert space, exponentially. So it's actually not that's not really a worry at all. It's just reflecting the fact that the n is the n plus one can be significantly larger than n. Yeah. So really what we want to see there is that we have that green line, that's for a noiseless simulation. And then on actual hardware, it's not scaling, it's not tracking that line exactly, but we see the same general trend. So even in the presence of noise, the effects of noise aren't enough to diminish the effectiveness of our sort of controlled interference.
Yeah, it's still increasing. If you look at it, it can be hard to see, but you're still getting an upward trend, and we would expect this to continue as we increase the number of qubits. All right, I will stop share so you can have back.
And see another question. So given the coherence times, roughly how many qubits do we estimate we can reach before decoherence and control noise wash out that advantage? That's exactly the question that's exactly one of the questions we're trying to answer and quantify, at least in this narrow context. Definitely beyond the 16 we're showing there. Exactly how far, I'm not sure, because we're continuing to iterate and refine the protocol that we've developed from this. So hope to have an answer for that soon. But I would say that the fact that we are getting this far is really a testament to the fidelity and coherence times that QuEra have been able to achieve with their analog hardware.
I agree.
Thank you. I think there's a couple more questions. I think they will be answered throughout the remaining of the session. So I think we can move on for now. Yeah. Thank you.
So
Thanks for those great
including
questions.
just for clarity, there is also a question on the Q&A, and I would like to suggest everyone, just for clarity on the priority of responding these questions, please use the Q&A rather than the chat, which makes things much more clear. And for the question that we have on a Q&A, I would definitely suggest that perhaps Jonathan addresses these two interesting questions during his presentation. Please, Edric, go ahead.
Yeah, well, there's some good questions in the Q&A. I'll leave those to Jonathan. Yes. So, encourage you to clone the repo if you'd like to follow along. We'll be specifically looking at the notebook in the PAWSY folder, analog combinatorial optimization. And for those who like to work with Python virtual environments, we have a requirements requirements file in there. So just to jog your memory, if you have you want to install that, just be Python pip install -r rex.txt, and that will install all of the modules that we use in this notebook. So we mentioned, or Tommaso mentioned earlier on that one of the applications being explored on QuEra is combinatorial optimization. And what this looks like in analog mode is choosing a particular arrangement of atoms in a 2D plane, and then evolving those atoms through time using pulses that parameterize this Hamiltonian. So we've got a term, which is a time-dependent Rabi frequency that's applied to all of the atoms. We have then we have a detuning term that shifts the energy at a particular atom when it's in its excited state. And then we have a final term, which are the van der Waals interactions between excited atoms. And we're working with these Rydberg atoms that were restricted for this picture to 2 levels. So our ground state and our excited Rydberg state. So through this, when you see the G there, that's our ground state. R, that's our excited state. So I think you can really see here, right, that our first term is driving atoms from the ground to excited state or excited to ground. And then these last 2 terms, they're influencing the relative phase of our basis states. Now, to do quantum computation, we need 3 quantum resources. We need superposition, we need interference, and then crucially, we need entanglement. And it's really entanglement plus those other properties that allows a quantum computer can go beyond just classical capabilities. And that's because we have this, once we're able to entangle our qubits, we're actually able to constrain the measurement outcomes on other qubits, essentially baking something like conditional logic into our program. Now, on a analog neutral atom quantum computer like QuEra, this entanglement is generated via the Rydberg blockade. Now, this is an effect that arises when we have 2 atoms that are sufficiently close. If we try to drive both of those atoms to the excited state, that'll incurs an energy shift that essentially pushes that state off resonance. And as a result, that transition becomes forbidden. So consequently, we'll only ever see one of the atoms excited and the other in the ground state. So we'll never see both of them elevated to the Rydberg state. You can see there, right, we've now have this ability to produce entanglement, right, between these 2 atoms within each other's blockade radius. So here we've got a small program written in using the blockade package. That's a package developed by QuEra for writing and simulating programs on the digital and analog system. Here we're using it the analog submodule, and essentially I've here just written a program which is a chain of 2 atoms with a lattice spacing parameter, and I'm applying a Rabi pulse for with a slope rising up of 0.05, a plateau of 0.15, and a slope going down also of 0.05, and a amplitude of 15.8. They're at the device limit. And what I can do is I can actually assign a value to the variable that I've specified, and then simulate that job for 100 shots. So if I run that, see I've got 42 instances of 1, 1. So that's the ground state in neutral atom conventions. Because, well, I'll leave the reasons for Q&A. And then we've got 33 instances with 1 at the rightmost atom, say, in the excited state, and 25 the leftmost atom in the excited state. And here I've run the same program, assigning a different lattice spacing to our 2 atoms. See, as we move further apart, keeping the same amplitude, we eventually see sort of a violation or a diminishing of that blockade effect. So we now have at a spacing of 8 micrometers, we're now actually seeing atoms in the doubly excited state. Now, the reason I emphasize this effect in the context of analog neutral atom quantum computing is that it means that the Hamiltonian that we saw there is a very natural. Sorry, it means that this effect we can actually use it to encode a very particular NP-hard combinatorial optimization problem. That's the maximum independent sets. So this is a problem that's very hard to solve, but fairly simple to state. Essentially, we have a graph like the one we see on the right here, and we want to find an assignment of vertices to 2 sets. So we are maximizing the number of vertices that are in different sets. And we're able to, for a planar graph, encode that into the Rydberg or neutral atom Hamiltonian using the blockade effect. If we position our atoms such that an atom representing a vertex is within the blockade radius of all of the atoms with which it shares an edge, the blockade effect will naturally enforce the maximum independent sets condition. So once we have that geometry, the challenge is then just to come up with the best set of pulses so that we can produce that we can guide our system towards this maximally independent state that's like natively encoded into our system's Hamiltonian. Just do we have any questions before I launch on? Cool. All right. Now, what's particularly neat is once we're able to encode one NP hard optimization problem into our system, we're able to actually, encode technically any other NP hard. We're able to tackle any other NP hard optimization problem by encoding it into a maximum independent sets problem with varying degrees of overhead. One problem that we'll be looking at in some detail is the max2sat problem. So this is another optimization problem that really arises. We see a lot in quantum computing as a benchmarking case, and it's another simple to state but hard to solve problem. Essentially, we have a set of logical expressions, the Boolean variables, where each of our terms consists of an or statement and then our two Boolean variables that are either negated or unnegated. And we want to find an assignment of true and false values to our variables that maximizes the number of true clauses or statements, with the assumption that we might not be able to satisfy every single one of the statements. So some of them might conflict. And this is interesting because it's used as a benchmark for classical approximation algorithms. So it gives us a point of comparison from our quantum computer to the best we can do classically. It appears, and it appears in a lot of simplifications of other optimization problems that we might want to address. So to solve this problem in an MIS framework, we need to map our set of clauses and the logical relationship between those clauses to a graph. And here, show that process where we're forming this thing called a conflict graph. So the idea is that for every one of our clauses, for each of the two variables in that clause, we add two vertices and connect an edge between any the vertices that are in the same clause, and then an edge between variables that conflict, right? So here we have the clause x1 is true, x2 is true, and this conflicts with this clause over here where x1 is false. So with this encoding, see here that any maximum independent set solution to this graph will also be a solution to our max2sat problem. Now, once we have that graph, we need to actually translate that to a physical geometry where we're going to approximate as best we can that conflict graph as a planar graph where our edges are sort of enforced or created by that blockade effect. Now, this isn't the way to do it, but I've just used a simple approach here where I'm using the network X to generate an initial layout of vertices, and then running a simple optimization loop to minimize the distance between edges that are connected, and then maximize the distance between vertices that are connected, and then maximize the distance between vertices that are disconnected. Won't go through the details there, but we can run this loop with our, our target blockade radius and a minimum allowed distance, build up a list of coordinates, and then here I'm passing those list of coordinates to the start class from blockade analog and adding those as positions. And here I'm printing out that geometry, and it's showing a layout here about particular atom positions. It doesn't come through too clearly with my dark theme, but if you can make out those purple dots and take a look at the graph here, you might be able to convince yourself that there's some correspondence.
So Adrian, I was going to ask
Pascal.
a question for maybe people who are not asking a question. So in this setup, you've chosen blockade externally from, or the blockade radius, external to the blockade infrastructure. So you just put 6.5 as a start point, right? And then the min being 6. Why 6? Would you get any errors if at this point if you actually had less than 6 as the minimum radius? Could you describe why you chosen 6 in the context of Aquila?
Good question. Well, it may actually be ideal to have a slightly smaller sort of target blockade radius, 5.8. But the radius chosen here, it's one of expedience, because it makes our simulations faster if we have a slightly larger distance. If we bring them in closer, the physics becomes a little more complicated. We have to pass a couple other options to our emulator, and it'll just take longer for people to run that in their in the notebook.
Okay.
So with this, we're able to go up to a larger number of qubits. Cool. So now we've got our MIS encoding of the problem that we've now converted to an atom layout. Now we need to actually construct the program. And what we're going to do is build a sequence of pulses where the goal is to minimize the maximum independent sets cost function. So again, that's simply, I want to reduce, well, I want to, on average, maximize the number of vertices that are in disjoint sets. So that is this sum here. And I'm using a minimizer. So I've just simply put a negative sign in front of that function. So here we've got the implementation of the cost function in Python and a second function to compute the expectation value, which we'll see later on is provided by a simulation using blockade. So far I've been a little bit vague on exactly what we'll be doing to evolve our system. We'll be looking at a couple options, starting with the canonical approach, and that's adiabatic quantum computing. So this approach, the goal is we're going to start off in an easy to prepare state, and then evolve the system continuously, changing it slow enough such that we hope that our system remains in that ground state. And the idea is we go from our easy Hamiltonian to our problem Hamiltonian, which encodes the optimal solutions in its lowest energy ground states. So we move slowly enough, we move adiabatically, we'll track that ground state, and at the end of the program, we'll have a high probability of measuring an optimum or close to optimum solution. So to just sort of visualize, what this pulse protocol looks like. So we're going to actually start off with a maximum amplitude RABI pulse or amplitude, and we're going to just ramp that down linearly to 0 across the duration of our program as we ramp up our detuning. Now, the way this works is at T0, when our RABI drive is at its maximum and detuning is 0. This is our Hamiltonian, right? And with the RABI drive maximum, dominating dominating the dynamics, and the interaction terms penalizing simultaneous excitations within the blockade radius, means essentially that means that our ground state is just our initial state. Every atom is not excited. Now, as we move towards our endpoint, T1, with the RABI drive completely switched off and our detuning at maximum, this is the Hamiltonian we're looking at, where we have this positive energy term for due to interactions between excited atoms in the Rydberg state. But we actually have this very, very large negative energy shift that increases linearly with the number of excited states. And our maximum independent set optimum is going to be a state with the maximum number of excited states within our blockade constraints. So that'll be the ground state of our system. So just to briefly go through the program, here I've defined sets of variables for my RABI pulse durations, the amplitudes, the detuning pulse duration and amplitudes, which I've just put together into an array of variables. I've going to make a program with the geometry we defined earlier, and I'm going to apply my my RABI pulses as a piecewise linear function with the duration specified by these variables, and values of the amplitude specified by those. Likewise for the global detuning. You can also construct programs by just passing the actual numerical values, but building it this way means we're able to run the program over an array of possible program times or ramping times. And I've just simplified that process using this little convenience map parameters function. Yeah, so I've already shown you the pulse protocol. So we're defined by one sort of our pulse duration. It's going to be a ramp going down, ramp going up. And yeah, here we'll actually run the program over a range of ramping times. And for that, I've defined this as objective function. So it's going to take our ramping time, map that into the format we need for the pulse times and durations, assign them to our program, and retrieve the results and compute the cost. Now, we're only taking 30 shots per measurement. So, we do see quite a lot of variance in our cost as we scan along these different pulse durations. But let's just take a look at the results for the minimum point in our cost. Right, so what we see in the output here, it's firstly, this is the results obtained from our simulation. So it's an ordered dictionary of bit strings, where again, a 0 is an excited state, 1 is a ground state, and the number of measurements. And I've run this here for 10,000 shots because we're doing a simulation. Simulations are cheap. And then below that, I've printed out the 2 most common solutions. So we've got the assignment there that's encoded. So here we've got an excited state in the this qubit and second qubit, essentially saying, okay, x1 is false, x2 is false, and here we've actually satisfied, with this assignment, we satisfy 3 out of the 4 clauses, which happen to know is the maximum we're able to do, because there's a contradiction, unavoidable contradiction in that set of 4. But yeah, essentially the algorithm has worked. We've been able to prepare a state with a high probability of measuring the optimal solution. Now, that's not the only way you could address the problem. It's definitely maybe the most natural, but I just wanted to end my showing how this can be extended. So here we're gonna see what we can do with a protocol that draws on the alternating structure of a Grover search or QAOA, for those who've heard of it. But we could essentially think of it as a quantum walk followed by a phase shift, so an operation where we shift the phase of all of the states, and then another quantum walk. Building the program is quite similar, except now got a slightly more complex pulse set of pulses. So here we've got a pulse, just the Rabi drive, followed by a period with detuning, Rabi drive at 0, and then another final pulse with the Rabi drive. Then, like before, we can run our program over a range of walk times. And again, we see a decent amount of noise or variance in our objective function because we're only taking 30, but still, let's take a look at the results we're getting at the lowest point. And again, we've managed to prepare, well, have a high probability of measuring an optimal solution to our max2 sat problem. And I actually think that, so it's with x1 false, x2 true. So we were to take a look at the solution we got with the other, x1 false, x2 false. So they're both equally optimal, but a different solution. So this is by no means the definitive way to solve the max2 sat problem. There are probably other gadgets or embeddings you could explore, but really wanted to just show you how, because we've got this really great native correspondence between the mechanism that we use in the system to generate entanglement and this hard optimization problem, we're actually able to solve and investigate a pretty wide array of difficult optimization problems. Thanks.
I just want to mention as well something interesting to note, right? So we've done in Edric's program, you can see it does blockade Python. So there's so it's running the simulator, the local simulator. If you translated these pulses to pulses on the system, right? If you ran on Aquila, it'd be something interesting to explore if you've got a bit of access time on Aquila. Because I think you might notice some differences in the different results because of different noises in the pulses. So Edric, do you have any comment about the more ramping, less ramping on Aquila in terms of like a larger complexity of a pulse state versus possibly shorter times? or longer times and less complexity of pulse state in terms of, let's see,
Well,
the noise that you get out of the system and how close you get actually to the noise being a subdominant, you get the right answer.
well, I mean, the impact of noise is it's a thing. It's it's very noticeable as you push out towards the maximum program length for
Yes.
for microseconds, and we also have to account for coherent errors. So if we look at how these these two algorithms have performed here, because that's what 15,000, let's say 16,000 shots of our optimal solution there. And then, okay, let's see the annealing protocol, probably round that also to it's about 16,000 shots. So we've got a similar amount of convergence. Okay. Um, so, but
But the
okay, how long
time of
is
year
our
is different.
program? So
Yeah.
how long is our program? Here we've got a runtime around about, say that's 1.8 microseconds. That's our ramp time with the adiabatic um, protocol. And if we take a look at our total program time, the walk, so what we've got, that's say about a 0.9 there. I can actually just put that into our plot. And we've got a total program runtime there of 0.16. So it's slightly shorter, but more complex. So now the question becomes, are the coherent errors, right? So that's like slight errors in our target amplitude. So not noise, but like errors in our target amplitude from shot to shot. For example, are they significant enough given the complexity of this, there's the sequence of pulses, that we lose that time advantage, right? So just like purely from a standpoint of the effects of incoherent, of relaxation, and like dephasing, sort of the noise, our walk-based approach might be more effective, but it has a more complex pulse sequence. So yeah, this is where you would actually need to sit down and do either some noisy simulations or just run it on hardware to actually really make that judgment. And that's the advantage, right, of being able to run on actual hardware.
Yeah, I would agree.
Answer these
And
questions.
then it's one of these things that for people who are experimenting, it's something you can give a try if you've got time on Aquila to really pose that and see. Because in this context, it's maybe not obvious, but in some other contexts, you might actually have pulse sequences that are quite long. If you can shorten the pulse quite a bit, let's say the runtime of the program quite a bit, but introduce a lot of complexity to the pulse state, it still might be worth your while to explore different avenues of generating a particular state. So it's something to consider for the people who are going to try to play with these type of the sort of state preparation to think about as well when you go to actual
And I would say, just from my experience, yeah, you can spend a lot of time thinking about this in the abstract, trying to work things out in pen and paper or on your notebook. But yeah, just actually being able to just collect experimental results, that'll often get you where you need to go faster.
Yeah. Well, I think that's our notebooks done and presentation done as well. So in which case I might hand over to Jonathan next to take over and to talk about Blockade Digital. We were just kind of playing with Blockade Analog in that notebook. So take it away, Jonathan.
Great, absolutely. Thank you, Pascal. All right. So I'm gonna so in the past session we were talking mainly about blockade analog and getting a bit of our hands dirty in terms of actually programming and executing small programs on Aquila. Now, in this next set of slides, I would like to talk a bit more about, I guess, the path to quantum utility that we see. I think both analog mode, digital or gate-based mode, as well as logical mode, neutral atom quantum computers, and how we see a bit about how we're getting there. So I guess this is goes in 3 parts. The first part is on analog mode and Aquila. The second part is the present on digital and gate-based mode, which is on Gemini, which is what Tommaso showed near the beginning. And then also I'll give some perspectives on some of our future updates on logical and fault-tolerant modes, and these logical fault-tolerant algorithms, which are enabled by error correction and fault tolerance. So maybe to begin, we can think about exactly what we're doing. I like to make things very physical by thinking about, well, we have qubits. Actually, these qubits are hosted by individual rubidium-87 atoms manipulated by lasers, where the qubit is stored into the electronic states of the atom, and then the qubit is manipulated by lasers, which manipulate the electronic state of that atom. Now, as both Edric and Tommaso said, our big product that we've had over the last several years has been Aquila, which is our cloud accessible computer, which you can access on Amazon Bracket, which implements these time-dependent Hamiltonian dynamics, where I guess you have this Hamiltonian H of t, which is basically you define your drive field, your Rabi drive, omega of t, which drives between your ground state and your excited state. And you have some detuning, which acts like an energy penalty, as well as some interaction term, which acts to actually impart entanglement upon your system. And unlike digital mode, where you program using these gates, you basically have this all-to-all, like an everybody gate, which basically does these non-trivial time dynamics, where you're able to program in your problem into the positions of atoms. Now, I would like to do a small shout out for those of you who are lucky enough to get the 1 hour free access. You guys will be getting emails soon. But actually, this uses a slightly different way of submitting jobs to Aquila. So I guess this is a bit of code that does that. First, you need to specify some environment variables for backend. Basically, you have some magic key, which is what you'll get in your email, which is what you have here, and then some other backends. Then, in this case, I just defined some arbitrary program just to make it work, and then you just submit your job through this exclusive access mode, which is actually the same exact way you would submit jobs through Amazon Bracket. You can imagine here it's program.QuEra.custom. If you're submitting through Bracket, it would be program.bracket.run, I believe, or program.bracket.run, I think. Right, and in this way, you're basically able to swap your backends for between emulation, which is what Edric showed, and hardware execution. Good. Now, maybe taking it back a step on what we've done with Aquila. One of the cool things is that Aquila has been out for over 2 years, which means we've been able to do a lot of very interesting and exciting science with Aquila. There are sort of three main areas which we have focused on. The first is optimization. So this is solving hard combinatorial problems using the sort of native features of hardware. The second is simulation, which is sort of in Feynman's vision, using a quantum computer to simulate quantum systems. And then the third is machine learning, which is, again, using the inherent quantum phenomena, such as entanglement and superposition, as a kernel or resource in a broader machine learning task. And I'll go over each of these, and hopefully I hope that this can inspire some ideas as to how to do these sorts of projects yourself, and maybe what to do on Aquila moving forwards. So the first is this maximum independent set problem, which is sort of the first big landmark result, which came out of Harvard in 2022, which is solving maximum independent set on unit disk graphs. The problem is basically, as Edric said, it is some graph problem where you want to select the largest number of nodes in the graph such that no two nodes in that set are adjacent. And this is called the maximum independent set. And it turns out that in this work, you show that there is a hint of a quadratic speedup over equivalent classical algorithms. And this is due to basically this quantum annealing and these adiabatic effects. Now, what we can do is we can actually go beyond unit disk independent set on our machine through 3 different methods. The first is on non-native hybrid algorithms, which is integrating your optimization into a larger hybrid quantum classical workflow. So, for example, now your quantum computer is now a subroutine in a larger, classical classical workflow. And now your quantum computer is basically giving hints to your classical solver. The second is on unit disk independent set encodings, which is to say you're able to reduce hard, NP hard optimization problems into optimization problems on unit disk independent set. And this means that, for example, if you want to encode some small Kubo problem, right? So quadratic unconstrained binary optimization problem, you're actually able to do so by modifying the weights of basically vertices on this graph, which can then be encoded directly onto hardware using our local detuning feature. And then finally, there's some recent work that actually merges optimization with machine learning using generative optimization, which is using the quantum device as a sampling kernel for an autoencoder. And then this lets us efficiently sample Boltzmann distributions. Good. The next major thing that we've done on Aquila is quantum simulation. And this has I guess this has been the main thing that we have done on the hardware, again, because you're basically able to find systems which are very close to the Rydberg atom Hamiltonian. And from there, you're able to simulate those analog, and this is analog, the equivalent systems using our quantum system. So for example, we have some cool papers on confinement and strength breaking, which is a topic of particle physics, frustrated magnetism, trimer spin liquids, quantum floating phases, so on and so forth, where basically we're able to explore fundamental condensed matter, field theory, particle physics, behavior using, lattices of atoms, right? So for example, here we might have some, canted lattice of atoms, and in this way we're able to prepare non-trivial ground states of these models. And typically this just uses, an adiabatic protocol where we start from the all zero state, which is easy to prepare, and we do some slow quantum evolution in order to prepare your ground state. And you can say do some quenches or other analysis to better understand that and probe that phase. Good. So the third thing that we've been actively exploring is something called quantum machine learning, specifically through something called reservoir computing, which is basically you use your quantum computer as a reservoir or a kernel in a larger classical machine learning workflow. So for example, in this case, we take some, we do some pre-processing, right? Say we take images of horses or say time series prediction, and we encode or embed these into Hamiltonian dynamics, right? So for example, we can encode those into the global pulse, the detuning as a function of time, like we might do for time series prediction, or we might, shift the position or local detuning based off of the image. Then we do some non-trivial quantum dynamics and then compute expectation values of the different atoms in the system. And then now what we can get is for each picture of a horse or a cat or whatever, we get a different feature vector. And then post hoc, without any variational optimization on the quantum reservoir, we're able to still train our system by training a set of classical weights. And actually, what's very exciting about this method is this bypasses several challenges with quantum machine learning, mainly the lack of need for any gradients or variational optimization on the quantum hardware. Instead, you basically pick a specific set of hyperparameters, and then you're able to just train on your system with that set of physically tuned hyperparameters, and you're actually able to get relatively good results in comparison to classical models. And in fact, these results are so good that it ends up being the largest successful quantum machine learning experiment to date, with 108 qubits. And that's shown in this plot here, which is again in this paper here, where as we increase the number of qubits, which is equivalently the number of features that we put as an input, we can compare, the QRC experiment, right, which is this orange line, to equivalent sort of best-in-class classical algorithms, which are an SVM or a neural network, where there you can see that basically your classical methods saturate at some test accuracy, which is again comes from things like overfitting and not having enough information in the system. And you can see that as we increase the number of quantum features, we actually increase and become competitive with the equivalent classical models. Good, which then brings us quite nicely to digital mode qubits. Now, again, I would remind that our qubits are made from individual rubidium-87 atoms trapped by laser tweezers and manipulated by lasers. But now, unlike the analog mode qubit, right, which is a ground state, which is weakly interacting, and then a Rydberg state, which is strongly interacting with the environment, right? Here, what we can do is we can basically drive dynamics between our ground state and our strongly interacting excited state using, some set of lasers. But now, what we can do for a digital mode qubit is we can actually encode our qubit into the two hyperfine states of this rubidium atom. And what this does is it makes it so that the effective qubit is extremely insensitive to the environment, because we're no longer using this Rydberg state. Instead, we use this Rydberg state only as a mediating state during a two qubit or multi-qubit gate in order to generate entanglement. And otherwise, your qubit is basically living in this ground state manifold, which means that they are very stable with a very long coherence time of order of a second. Good. Now, one of the key features, which is sort of made this quantum computing system very exciting, is something known as the Rydberg blockade, which is to say that because of this strong Rydberg interaction, only one atom can be in the Rydberg state at a time. And then we can actually use this to robustly generate multi-qubit gates by basically excluding certain states from dynamics. Now, this is actually a picture from this recent paper from Harvard. I guess this was 2 years ago now, where it's individual atoms, which are 2 microns apart, and then spaced 10 microns apart. And then you can basically act on pairs of qubits, and then basically you hit it with a laser, right, going from side to side, and all of the atoms see the same laser, and then therefore all of the atoms see the same gate, and basically adjacent pairs strongly interact and get enacted with this multi-qubit gate. And we see there that actually in this Harvard demonstration, they found that they were able to get a 99.5 fidelity control Z gate. Now, the other cool thing about these qubits is because you just need to bring atoms close together, you can also do multi-qubit gates as well. So for example, if we bring 3 qubits together, we can also do a 3-qubit gate, say a CCZ gate, or 4 or a 5 or a 6 or so on and so forth, as long as we're able to bring these qubits together. And in fact, in this recent Harvard paper, they found that there is a 97.9 fidelity CCZ gate as well. And what's actually exciting about this is actually when you sort of compare these numbers of how to decompose a CCZ gate into a CZ gate, plus all of the moves and gates that you need to do, it turns out that it may be competitive to actually just directly do the CCZ gate instead of the CZ gate. Good. Which brings us then to our native gate set. If we're starting to think about how to actually program our Gemini hardware, we need to have a universal gate set in order to do universal computation. So the first and most natural gate is the controlled Z gate, and then possibly things like the controlled Z gate. And then, maybe in the future, as we increase our capabilities, we can get, control Z gates. In principle, this is actually, you can generalize this to something called a permutation symmetric Z phase gate, but maybe that's too much detail. But then the thing that makes this computer universal is then we can also do arbitrary 1-qubit rotations on any qubit. Good. So the exciting thing about these this hardware is something known as a zoned architecture, which is to say we're able to position our atom traps in 2D space, and we're able to organize this so we can separate this into some storage zone. We have some large and scalable sort of place to store all of our atoms. Then we have some entangling zone. We're able to entangle many qubits in parallel at the same time. And maybe we can have some readout zone. We're also able to measure and do feed forward of the system. And in fact, this is the architecture which we are implementing on Gemini, which is, I guess this is the picture here of this is the picture. This is what the architecture we're implementing on Gemini, which is currently under development at ICE. Now, I think I'm a big proponent for pictures worth 1,000 words. So I guess if a picture is worth 1,000 words, then animations are 60,000 words a second. So I guess I'm going to show you some animations of how to move our atoms around, right? So here we have our storage region and our entangling region, and we can basically specify our SLM sites, right? And then we're able to use a dynamic AOD to pick up and move our atoms, in the middle of the circuit, right? So these are coherently holding our quantum information, and what we can do is we can move our atoms around, right, and move them from the gate region to the storage region, right? And then once they're in the gate region, we can do a gate, which is the laser pulse you see there, the red flash, and then we could move them, from the gate region, back to the storage region, and in this way, we actually can get sort of, if anyone asks about our connectivity, we don't really have a connectivity in the native sense of, say, a superconducting device because of this reconfigurable architecture. Good. So maybe to recap these highlights, the first is to really think about why neutral atoms are sort of an exciting way to do gate-based computing. The first is that they're high fidelity, right? So they have a very long lifetime and as well as a high fidelity 2-qubit gate. Next, they're massively scalable, which is enabled by optimal control. You can have many qubits, many sites, thousands of sites with very few signals by basically just using, centered, optical control techniques. Third, you can have this non-local connectivity enabled by these reconfigurable atom arrays, which means that you're able to just not necessarily think about the native connectivity of your underlying device and think more abstractly about, just like, oh, I want to do a gate between qubit 3 and 7, and then it can just do that. And then finally, and I didn't mention this as much, is this notion of parallelism, which is to say, you basically want to be doing many CZ gates in the gate region at once as possible, right? So now, if you sort of if you allow my stylized version of a circuit, right, you might have your 1-qubit gates, right, and then you have a bunch of parallel 2-qubit gates, and then 1-qubit gates, and 2-qubit gates, and you repeat this until your program is complete. So this is sort of why Gemini, I guess these are the reasons why I'm very excited about Gemini, because basically of these 4 capabilities that are sort of unique to our architecture. Great. Now, if we think about circuits, right, and NISQ approaches, the field is quite mature in terms of NISQ era algorithms and applications. These also follow the line of optimizations, simulation, and machine learning. Right, for optimization, we have our favorites like QAOA or quantum enhanced Markov chain Monte Carlo. For applications, like portfolio optimization and so on and so forth. Next, there's simulation, where we have our old favorites like variational quantum eigensolver and trauterization. This lets us do things like Ising simulation, molecular ground states, maybe trying to find surrogates of real-world models like, say, options pricing or other critical behavior. And finally, we can also work on things like machine learning. So again, inheriting the same gate and NISQ era approaches from other modalities, we can also execute these here while leveraging the strengths of our hardware for things like digital neural networks or digital reservoirs for tasks like classification, regression, prediction, anomaly detection, generative machine learning, like unsupervised learning, and anything that you might have tried on another gate-based device. Gemini will hopefully also be able to execute on this as well. Which, of course, brings us to the future of logical mode qubits. So if we think about qubits, right, we think of some abstracted object, right, which is, some state which is either 0 or 1 or in some superposition of both. And now what we can do is, instead of encoding this into the electronic levels of a single rubidium atom, instead we can encode a qubit into the electronic levels of a large number of rubidium atoms. And what this does is it makes it so that you're actually robust to errors which may happen to these atoms. So for example, maybe, a stray photon comes in and flips this rubidium atom from 1 to 0. Well, what we can do is we can use something called quantum error correction to basically detect those errors and correct them and make it so that actually our computation is stable even under external noise. And this is very similar to classical error correction, where, for example, there you might have something like a repetition code, right? Where if you want to transmit a 1 or a 0, you can instead say 1, 1, 1, 1, 1, or 0, 0, 0, 0, 0. And then basically you take the consensus on, did you say more ones or more zeros, right? So then even if I flipped 2 of those ones to zeros or zeros to ones, I can still recover my signal. And you can do, actually, turns out you can do the same thing for qubits as well as bits through quantum error correction, though it's a bit more complicated because, unlike classical error correction, you have things like the no cloning theorem, as well as the non-community of observables, where, like, if you measure, the x basis and the z basis, then it messes things up. So nonetheless, basically what you can do is, using these techniques, you can encode a single qubit into many logical qubits. And in fact, neutral atom systems are at the forefront of doing this logical mode. And this is because we have something special that no one else does, which is atom reconfiguration. So for example, suppose we wanted to take one logical qubit block, right? Say this block of atoms with another logical qubit block, and we wanted to do some entangling gate. Well, it turns out that one way to do that is something called a transversal gate, which is to say you basically do a physical gate on every single pair of atoms in the two codes. And how do we do that? Well, we move the first atom in the first logical qubit down. We move the second logical qubit down. We do our gate, and we move it back into the storage region. And in that way, we're able to very efficiently scale to very large numbers of atoms, while still also efficiently having a lot of efficient parallelism in order to hopefully scale to rather large code depths. Now, okay, so this was in the abstract. Now let's actually put this in more physical context, right? And this actually brings us to a recent demonstration which we did on hardware. And I guess the challenge here is that for our true quantum utility, we need efficient error correction, right? Now, the one primitive you need for fault-tolerant computation, and this is maybe ends up being a bit more complicated, is something called a magic state. And what a magic state is basically a resource state for computation. And this is based off of this Eastman-Nil no-go theorem, where basically you need to have a universal set of gates, but it turns out these cannot be transversal, and typically it's something called Clifford plus T, which is to say you have Clifford gates, which are actually easy to simulate classically and easy to error correct, and then you have T gates, which are hard to simulate classically and a bit more difficult to error correct. But then what you can do is you can do something called T-gate teleportation, where instead you can prepare these so-called magic states use to generate these T gates in order to do your universal computation. So in this way, we can basically prepare these magic resource states as a resource for computation. Now the challenge, of course, is that in preparing them, right, we're also stuck with noise and decoherence. So we can then do something called magic state distillation, which is, I guess, a recent paper that we published at the end of 2024, which is the first experimental demonstration of magic state distillation using our hardware. And this was done, on this machine right here. And what we do is we have some low fidelity magic state, right? So you can imagine I have the block sphere and I have the vector of my state on the block sphere, which instead of being a perfect fidelity state is sort of smushed over some area. And what I can do is I can then basically, through measurement and decision, I can take, say, 5 of these low fidelity magic states and distill them by basically measuring and doing some corrections, distill them into a single higher fidelity magic state, right? So I have some low fidelity state here with some higher entropy, and then I turn it into a single lower fidelity state. And you can imagine if I do this many, many, many times, I can suppress any physical errors to whatever order I want to actually do some very deep logical fault-tolerant computation. And in fact, this is what we did on our hardware, where we had some, logical qubit, which was encoded out of physical qubits. In this case, we used the D equals 3 color code, right? So this is a 7 qubit code, or the D equals 5 color code, which is a 17 qubit code. And we actually tailored the quantum circuit execution perfectly to our hardware, right? Where again, now these animations are again pictures of individual atoms, right? And we're actually, this is, I guess, not real time, obviously, but the actual execution of how I'm doing my logical circuit, right? So first I prepare my logical qubits, and then in the next step, I then entangle my logical qubits in order to do my magic state distillation. And in this way, we're actually able to show that we have, an 8 times gain in the magic state fidelity from distillation, which actually tells us we did actually improve and actually demonstrate that, we have some small logical primitive, which is this magic state distillation, and we got some improvement in actually executing these algorithms. And this is exciting because, maybe it's not your 1,000 qubit, QPE or, other fault tolerant algorithm, but it's an important subroutine in basically every single one of those algorithms. And I guess this is the sort of the killer plot here, where this is basically your injected input fidelity of each qubit, and then as you increase basically the acceptance rate, right, you can actually get break even, which is to say, after you distill your qubit, you get a higher fidelity than your input fidelity. Good. And then maybe as one last thing to mention would be actually transversal gates give us some pretty neat things we can do in terms of decoding. And I guess this is just a quick shout out to something called correlated decoding, which is in conventional decoding architectures, which is to say you have some errors, you want to detect and correct those errors, but it turns out to be a hard computational problem to go from basically the indicators of those errors, called the syndromes, to the actual corrections you need to do. That ends up being a hard computational problem. And we've actually made it maybe a little, maybe a little bit more complicated, right? Which means, we need more computational power. But at the cost of actually doing many less rounds on the quantum hardware, which means that instead of going from order D error correction rounds, you can do everything in order 1 error correction rounds by basically looking at the entire circuit and basically tracing out how all of the errors might flow. And this turns out to be, a 10 to 100 times logical clock speedup in this fault-tolerant regime because we have these transversal gates. And, this does make the problem harder. But I think, one thing that's nice about classical computing is you can get a whole lot of it. There are, of course, challenges of, now you need to be doing this at, hundreds of microseconds or tens of microsecond scales in order to get real-time feed forward. But nonetheless, these are, solvable computational challenges. Good. And now really to think about what this gives us, right, is once we have error correction, right, this means we have real quantum utility, right? Like if we have, 1,000 or 10,000 error corrected qubits, we can do some very exciting things. For optimization, there's some neat things and things like decoded quantum interferometry for research and so on and so forth. Simulation, we can do things like molecular ground state characterization, material simulation. For machine learning, we can do all sorts of very cool things with like algebraic and structure problems, topological data analysis. I can sort of go on. And of course, there's always the spooky like code breaking and, breaking RSA, as well as if we get the quantum internet going, we could also do real quantum information processing from quantum sensors. And this is what is enabled by this real quantum utility. And now maybe to conclude, I'd like to sort of think about maybe a call to action on what we can think about for the next, say, 3 to 5 years as we build out our next generation of hardware, right? And now this is, if we have tens of logical qubits, right, we can think about, demonstrations, right? Like, yes, we can do magic state distillation. Yes, we can have, log-live qubits, or we can have, small algorithms. If we have 1,000,000 qubits, of course, we can do some very powerful things, right? We can simulate our, Hubbard models and figure out room temperature superconductivity. We can, factor large numbers and, break encryption, all sorts of very cool things. For thousands of logical qubits, this is our early utility. But now the real question is when we get to the hundreds of logical qubits, right? What can we do with that? And I think this is really a question that I have, which is what can we do with 100 qubits, right? What can we do with 100 logical qubits, right? For in this logical qubit era, but then also backing up from there, what can we do with hundreds of physical qubits, right? Which is what we've been exploring in the NISQ era for the last, say, 5 or 10 years. And what can we do with hundreds of analog mode qubits, which I think we've answered pretty decisively of we can get interesting special purpose utility today out of these analog mode devices. So maybe with that, I'd like to conclude. And I guess if people have any questions, please write so in the chat, and I'd be happy to answer.
Thank you so much, Jonathan, for the very interesting presentation, and of course also to Edric and Pascal for the previous part. I wanted to perhaps ask you, Jonathan. There was an interesting question on a Q&A. If you can comment on those two things. The first one is how can we design efficient initial state and ansatz for random Hamiltonians? Can we start with that, perhaps? And
Sure, yeah. I touched on this a little bit when I commented about reservoir computing, which is, I guess, one of the main challenges with especially today's variational algorithms is that we have something called barren plateaus, right? Which is to say that the gradient is exponentially small for sort of typical states, and then which means you need an exponential number of samples to get out of that. And actually, one of the things which has informed a lot of our algorithms development for neutral atom computers is that our sample rate is rather slow in comparison to other to superconducting devices, which means that we need to be designing around, sample sparse or sample sensitive, algorithms, right? So actually, things like reservoir computing, right, is gradient free. Like you do not need any, variational optimization, right? And similarly for, other algorithms, for example, QA, it's sort of taken for granted now where you can transfer one set of parameters to another set of parameters, right? So I think while sort of these variational algorithms and barren plateau problems are certainly challenges, they're definitely also surmountable challenges. And I think actually by having access to real world hardware, this actually lets us actually design algorithms tailored to that hardware and really go in for this notion of co-design, like really get the most utility we can out of today's devices.
Excellent. Jonathan, the second quick thing that our colleague asked, how can we achieve scalability for Hamiltonians involving large number of qubits? And I guess you can answer this question on two different levels, at least one from the hardware side and the other one on the software side, perhaps, and also involving, for example, decoding, which is one of the central elements regarding quantum error correction that we didn't have, of course, time to cover in depth in this presentation.
That's right. So first from the hardware side, one of the very exciting things about neutral atoms is basically everything is just like optics, right? There's lots of hardware surrounding to make sure all of your optics do the right things, but the actual computer is basically just a bunch of atoms held in a vacuum, right? And what this means is you can then scale the number of traps, which is equivalently the number of atoms, which is equivalently the number of qubits. You can scale the number of traps to thousands or tens of thousands relatively easily, while also preserving the amount of control. So you don't have to have 10,000 wires going into your device. And what this means is we're actually sort of relatively easily able to scale to a large number of atoms. And I think that sort of gets to some of these scalability questions, especially for fault-tolerant algorithms, which might require millions of physical qubits. Right. Now, the next question is one of scalability on the algorithm sense, right? And I guess this can go many, many different ways, right? For example, if we want to be really sensitive around phase transitions for different Hamiltonians, right? Suddenly your correlation length diverges and your 16 by 16 lattice, analog mode lattice is no longer able to sensitively probe conformal field theories, right? Because now the correlation length is larger than the size of the system, right? But then that's really where the interesting physics starts to happen, and that's where you might need to have the hundreds or thousands of atoms. But then maybe the other half of this question is on the digital side, where now we maybe have 100 or 1,000 qubits. And there, again, it's tailoring these algorithms so that you're not sort of wasting them and you're still able to sort of extract the hard piece. And yeah, so and then I think the third is then a completely tangential, Tommaso, which is decoding, which is now basically it's a very hard computational task to basically go from errors on your logical qubit to, or which are called syndromes, to the actual corrections you need to make. But actually, it turns out that these are basically like decoders, they're called, right? So it's basically you take some syndrome and you decode that into, based off of some noise, right? Some model that you have in your mind, right? Based off of that model, you decode it into a set of things that actually happened, right? And that's actually a very specific thing because actually here you have some, signal and you want to be able to translate that into a different signal. And all of a sudden, that sounds like AI. And actually, this is some of the stuff we're doing. We had some work with NVIDIA a few months ago on basically using machine learning techniques for decoders, right? Which is to say, you have some GPU sitting very close by to your QPU, right? Which is now on a very fast link, right? On the order of microseconds or tens or hundreds of, actually don't know exactly the scale, right? And now you're able to extract those errors, decode them on the GPU, feed them back into your device, and then in real time make sure your qubit stays alive. And that ends up being part of what we're doing for our fault-tolerant research.
Yeah, I was gonna add on to that.
Yeah.
It's actually quite an interesting aspect of trying to get the scale up. This is why I think co-design as a quantum supercomputing center is kind of critical, because essentially, especially in the error correction regime, you really need heavy compute, training models, figuring out exactly what the noise is, figuring out what a syndrome is, doing the correction fast, dynamically. I mean, in at least in the case of neutral atoms, it's not like an atom will suddenly have a bias. An atom is an atom, thankfully. They're not like funky other possibly more complex sort of qubits, as it were. But you can have other things that introduce bias and sort of some pulsing operations that could be quite complicated. You want to constantly evaluate. So this is where I think in terms of real scalability, there'll be the physical qubit scalability, the compute scalability that makes sure that you can get logical qubits, or at least not particularly noisy qubits, as all part of this. And it will require quite a bit of co-design with a lot of different expertise to kind of hit that scalability factor. There's another thing as well, in that I think like if you gave people 1,000 qubits now, there'd be some algorithms they know okay would work, right? But that algorithm that runs 1,000,000 qubits is like a novel arm. Since no one is capable of simulating that, no one's really explored that space, except in some specific mathematical ones. We're like, okay, if we got more qubits, we know we could do better. So there's a lot of also in terms of scalability, just new algorithms and algorithm designs that make use of stuff rather than just normally scaling up. And this happens also in HPC, right? People are like, oh, I got more GPUs. You're like, yeah, but your code can't scale because it's like limited. So great. And there could be novel things of just doing lots of different circuits at the same time, shot parallelization, other things as well that in principle could happen as maybe an easier sort of low-hanging fruit once things get to large early utility algorithms. So there's a lot of space to explore as we scale up, but it really requires co-design from a variety of different fields.
Thank you, Pascal. Maybe I can stay with you just for 30 more seconds, perhaps, and just to comment on a question that we received on the chat earlier regarding an observation that I made during the first part of the presentation in the introductory part, saying that our quantum computers based on our technology, are actually extremely energy efficient in terms of power consumption compared not only to other quantum platforms, but also, and probably most importantly, to other classical supercomputing systems. Can you perhaps try to provide a slightly broader overview with some technical data on
Sure.
this particular issue, so that everyone that is listening to us can have access to this?
Yes. So, I mean, it also comes down to, let's say, quantum utility. So one of the challenges in terms of quantum simulation, I mentioned it's computationally challenging. It actually has a large memory footprint. So if I want to run an equivalent quantum simulation, there's quite a lot of computing resources I need. And in general, also classical algorithms as well, right? Generally, if I have a GPU that consumes a couple of 100 kilowatts of power, then if I want to increase the performance boost, I might have to add a couple of 100 kilowatts of extra power, right? So every single compute element keeps adding more, and I don't necessarily get a trivial doubling of compute power that I would in a quantum qubit context. So if I look at the supercomputing cluster that's dedicated to quantum computing simulation, which is Ella, which is 8 nodes of Grace Hopper GPUs, it actually consumes thousands of kilowatts of power at maximum peak usage. Now that's less than Aquila, but if I want to add another qubit to the, let's say, Gemini, I don't have to double the power, but I would have to double the power in terms of the equivalent quantum computing simulation. So very quickly, there's no way to kind of trivially grow computing power and keep the power envelope the same. It has, if you add more compute, things get more energy efficient, but you still have to add another GPU, another CPU, and power that fully, and then suddenly you get the extra bonus computationally. Whereas in, at least in the context of neutral atom-based muons and so on, other technologies, if I want to add another qubit and get a doubling of, in principle, computational resources, I don't have to increase my power envelope, right? The lasers are there, they're on. If I have 1 qubit or 200, the lasers have to be active in this context, right? So you're still powering the system. And that's not the case at all for supercomputing resources. It's actually one of the challenges in the current supercomputing landscape is powering the new systems. So there are exascale systems, right? 10 to the 18 floating point operations per second systems in the US. There's sort of exascale systems that are happening in Europe. They all are consuming, 20,000 kilowatts, 30,000 kilowatts, 40,000 kilowatt hour, like per kilowatt hours and so on. So they consume huge amounts of energy. Even the data centers that people are sort of not necessarily aware of. If I look at a data center, if I look at some of the new data centers that Amazon and Microsoft in terms of Azure are planning, they're thinking power plant for the data center because the data center is consuming tens of megawatt scales of energy. That's huge, right? That's a very large energy footprint. If I want
Right.
qubits, I'm still at 10 kilowatts for this type of lasing system for Aquila. So it stays 10 kilowatts, kind of, maybe a little bit more, but there's not a huge blowout of power.
In fact, just to add to that, one thing that's sort of interesting is actually the system is basically consuming this power at all times, right?
Yes.
Because basically it doesn't matter if you have a computation or not, the lasers need to stay on, because this is how they stay stable. And actually that 10 kilowatt number, that's not just like 10 kilowatts of lasers, that we do have some pretty intense lasers. This is really like an all-in number, right? Like keeping the lights on in the lab, but like keeping the air conditioning on. So like it's actually a very like minimal amount of power that we're really considering here.
Yeah,
And
and
maybe
sorry, go ahead. Marcel.
no, I just wanted to also let Min-Ho comment on this specific part of our technology, who is the head of laser systems, and perhaps Min-Ho, you can comment briefly on the current challenges, bottlenecks, and opportunities of using actual lasers compared to other devices and platforms that are targeted toward quantum computation. How can you elaborate a little bit more on top of Jonathan and Pascal's comments?
Yeah, so this is great point. So let me think about it. So I think one of the advantage of neutral atoms is that the number of controls, compared to other like superconducting technologies, we don't need like growing number of electronic wires to support like qubit scaling because we control everything with light. So that's one advantage. I think I have to say that nevertheless, we still need to be able to control individual laser spots and then be able to address qubits in very stable way. So that will be one challenge. And the other thing is atoms are we still need to maintain the lasers in very stable fashion while keeping them while keeping their laser power enough to support multiple entanglements at the same time. So there's some kind of competing challenges there. Let's say, yeah. But I think the opportunities here is our modality compared to other maybe electronic control modalities. The scaling is a lot more favorable. The number of classical control is a lot fewer than other. Yeah. Okay.
Fantastic. There was I would like to just quickly slowly change gears, we had an interesting comment and question in our Q&A panel from a senior undergrad in physics and that is starting a master's in EC with a focus on photonics and optics. And the question is about some recommendations on resources, books, papers, videos, and so on. And maybe we can ask, we can respond from the perspective of QuEra, but also from the perspective of POSI. And you, Pascal, put a lot of emphasis on the opportunities that POSI is offering to prospective users. So from QuEra's side, what I can definitely say is that there are a lot of interesting resources on our website. We also have a very interesting GitHub page where we post a lot of interesting examples that are dedicated to our technology. What about your side, Pascal? Can you comment on the resources that could be available to these students and prospective users of our technology?
Yeah, so I will comment first on the resources in terms of just learning. So Edric has the notebook that we shared here. We do have notebooks. There's actually a couple of repos that are usually research projects, so they're not necessarily documented as much, but they usually go through some of the logic of how we implement a problem on the analog systems. And for digital systems, it's a digital system. So in principle, the QuEra is probably the best place to look at some of the implementation aspects. But in terms of resources, right? So POSI is very keen on democratizing access for researchers and even students. So we run internship programs, actually. So during the summer holidays in the Southern Hemisphere, there is a POSI summer internship program. It is actually limited to students going to Australian universities, but part of it might expand out. And the idea there is to provide not just access to some of the papers and references and so on, but actually get a hands-on experience of actually being able to run simulation. So that is an interesting challenge, because if you're exploring qubits, you might be fine on your laptop with 5, 10, 15 qubits, but then it's possible the algorithm requires 36, and at 36, you're really struggling for compute resources to run that. We're trying to look to offer our simulator for access. Again, it's principally to Australian researchers, but the model we have, we're trying to make sure that we are sharing this idea, this approach that we have with other computing centers in the world, where we also are looking at, as I said, this access model for true quantum hardware, so you can get that real world experience. Because even the example that Edric had, right, you're looking at pulse controls, and there's two approaches that essentially give you the same result. In ideal world, you're getting the correct solutions, and you're getting the two sort of correct solutions at roughly the same sort of rates. That's great, but then there is really playing with hardware, which can be interesting till you get to logical. I don't know if we'll ever get to fully logical, but we'll get to very logical-ish qubits, right? You still really want to understand what's going on in the noise. You still want to play with that. So we want to make sure that we provide access models. Like if you're starting up a master's thesis and your supervisor is like, I actually would like to do something, and there's like a research project, I've got Australian collaborators, then it's a real way of also us assisting a research project to really get off the ground, get access to resources like simulation, but also get access to true quantum computing resources to run on Aquila for a certain number of hours. Once an initial exploration is done and you've worked out sort of what you want to do on the actual hardware. So I'm going to say, especially if you're starting up, I mean, one thing if it's sort of a master's and it's a research project-ish oriented stuff, that's great. We're kind of in the quantum computer. If it's more in the photonics aspect, then probably the best person to ask is Aquila, if they have any internship programs for the Minho, right? Maybe he needs someone who understands lasers. That's not what POSI does. We're happy for other people to do lasers. We're kind of interested in the software and algorithm design.
Yeah, that's correct. So just to confirm, so at QuEra, of course, we have internship programs across different areas, hardware, software, and applications, and just feel free to reach out to us and check our website for further information. So with this, I would like to thank all our guests, Pascal, Minho, Jonathan, and Edric, for the excellent presentations that we have heard today. Just for the attendees that are still online, if you weren't able to follow in a very detailed way all the parts of this session, feel free to check the YouTube video that we will post soon. And for the Korean community, we'll be happy, Minho and myself, together with our colleague Ayumo, to see you at Quantum Korea and the related events that were advertised at the beginning by Minho. So with this, I would like to thank you again for your participation, attention, and the very interesting questions that led to this very nice discussion at the end. And hope to see you soon again, either in person or virtually. Thank you so much, and have a good rest of the day. Bye-bye.
Thank you.
Bye-bye.